Hello, advanced geometry students. Welcome to a beautiful day of home learning here. And today we're going to talk about section 12.2, which is applying what you learned from 12.1 about right triangle trigonometry. So today we're just going to talk about some application problems where you could use right triangle trigonometry to solve for some unknowns. So first, a little bit of vocabulary. All right, so some stuff you'll read in problems with trigonometry often called angle of elevation and angle of depression. So we're just going to draw a little rough sketch, kind of show you what those things mean. So first, an angle of elevation. Angle of elevation is the angle that you would look up from your natural horizontal line of sight. So here's the ground here. Suppose I'm just chilling, stick figure style. It's pretty good, huh? And then there's a bird. All right. Let's actually make the bird flying higher up here. All right. So normally, my line of sight is horizontal, looking around. This is my normal horizontal line of sight here. If we get the right arrow, there we go. All right. But in order to see this bird, instead of looking out horizontally, I need to look up. And that angle that I looked up is referred to as an angle of elevation. So change this back. So this angle that I looked up from the horizontal is the angle of elevation. Remember, this represents the horizontal. And this is my new line of sight. And again, sorry about my bad handwriting here. All right, so an angle of depression is very similar. All right, but rather than how far you look up, it's the angle that you look down. All right, so suppose that, let's say, Nico is out hanging out on top of a mountain. All right, so let's draw Nico here hanging out, enjoying a beautiful day, and I'm down here in the valley on a hike with my calculator doing some math problems. All right, now Nico, his normal horizontal line of sight out enjoying this beautiful day will be out that direction, but Nico looks down, he sees me, and of course he becomes depressed. So here we go. This is the angle of depression, the angle that he looked down. And again, this is compared to the horizontal. So the most important thing with both of these is when you're reading a problem, if it refers to an angle of elevation or an angle of depression, you always compare it to the horizontal. When we're doing an example in just a moment, I'll show you the most common source of error. But when you read that, you just compare that angle to the horizontal. How far you looked up from the horizontal is angle of elevation. How far you looked down from the horizontal is angle of depression. And one other thing that we can apply here is that, we learned earlier in the year that when parallel lines are cut by a transversal, alternate interior angles are congruent. So in this diagram, we have two horizontal lines, one out from the bird and one from the cat. And of course, two horizontal lines are going to be parallel to one another. All right, this line of sight between the two would act as a transversal. And so we would know that this angle of depression would have to be congruent to this angle of elevation. So in a problem, if you're given an angle of depression, you could always put that same angle as the corresponding angle of elevation. And again, in just a moment, I'll show you how that works. All right, so let's look at some examples. So Lee is standing on top of the school at a height of 100 feet. All right, so let me do my best here to draw the school. So here we go. Here's the school. And we need some ground here. Let's draw the ground. All right. Here's Lee. She snuck up on top of the school to get a good view of the city, and she's 100 feet up in the air. So I know that this distance is 100 feet. All right. She looks down at an angle of depression of 65 degrees. So this is where we're going to see our most common source of error. So check it out. Remember, Lee's normal line of sight, is horizontal. All right, but she looks down at an angle of depression of 65 degrees to see psi shri. So she's looking down 65 degrees to see, we'll put psi shri like right here, psi shri. So in this problem, this angle is the angle of depression. All right, so how far is psi shri from the base of the school? I want to find x. Now we're going to make some assumptions when we're doing these application problems. Things that you would consider to be perpendicular to the ground, you can assume they are. For instance, the school is perpendicular to the ground. And so the reason for that is because now what we want to do is we want to take this situation that we've drawn a little sketch of, and we want to find a right triangle that models it. So notice, here's my right triangle that kind of models this situation. All right, so we know that we have a right angle. We know Lee is up here. We'll call that point L. And we know that this is 100 feet. We know that psi shri, or point S, is here. And we know that, we'll call this like B, the base of the school. And we know this is what we want to find. Now, in the given problem, this angle of depression was 65 degrees. Now you'll notice the triangle that I've drawn is this right triangle. And that 65 degree angle is not inside of that right triangle. So rather what I'm going to do is I'm going to use alternate interior angles to take this angle of depression from Lee and make it equal to the angle of elevation from psi shri. So this would also be 65 degrees. So now in regards to the right triangle that I'm going to use to solve the problem, I now have an angle that's inside of that triangle. So I'm going to put my angle of depression here as my angle of elevation from psi shri. One other option you could do is that you could use this angle because you know that these two would need to be complementary. And so this would have to be 25 degrees. And you could put 25 degrees in here and you could use that angle instead to solve the problem. So the idea is to draw a little sketch, get a right triangle that has at least one side length and an angle measure, or maybe you have two side lengths, you need to find an angle measure, or whatever, just enough to do some trig, and now I have enough to do that. So here's the trig part. Relative to this angle, the 100 is the opposite side length, and this x that I want to find is the adjacent leg. Remember, I do not know anything about the hypotenuse. It's irrelevant in this problem. So then I'm going to go back and I'm going to think about my little acronym of SOHCAHTOA. And which one of those things uses A and O? Well, that's tangent, the TOA one. So I'm going to say the tangent of 65 degrees is equal to opposite over adjacent. And now I'll use my calculator to solve. All right, so real quick, remember, make sure your calculator's in the right mode. A quick test is that the sine of 30 degrees should equal 0.5. So when you type in sine of 30 in your calculator, if you don't get 0.5, then you did something incorrectly. All right, so be careful that you are in the right mode. And if you need help changing the mode in your calculator, just shoot me an email and I'll see if I can help you out. So to solve for this, remember what I taught you last time is I can just swap the trig part with the variable because the variable is in the denominator. So x will equal 100 divided by the tangent of 65, and 100 divided by the tangent of 65 is around 46.6 feet. It doesn't say how to round, so we'll just leave it at nearest tenth, I suppose. 46.6 feet from the base of the school. Here we go. All right. We can also use this to work backwards to find angles as well. And that's what the next example will be. All right, so here we go. A plane begins its descent from a height of 30,000 feet to land at DIA. So first, let's start off with some ground here. All right. Remember, I'm a flat earther, as I've told you before, so we're just assuming the earth is flat here. All right. Duh. All right, here we go. So the plane is flying around. Here's the plane. All right. And here's DIA down here. All right. Now that plane is flying at an altitude of 30,000 feet. So I'm going to draw that perpendicular to the ground. Remember, an altitude we know is perpendicular. So we can call this 30,000 feet. Let's see. If the ground distance from the spot below the plane to the airport is 108 miles, all right, well, this is in feet, so I need to have the same units. So the first thing I'm going to do is I'm going to convert my 108 miles to feet by multiplying by 5,280. So 108 times 5,280, which is how many feet are in a mile, is 570,240. So rather than 108 miles, we're going to use 570,240 feet for that ground distance from below the plane to the airport. What is the angle of elevation from the airport to the plane? So somebody's chilling, standing here at the airport, and they want to look up and they want to see that plane. I want to know what's the angle of elevation up to the plane relative to the horizontal ground. So in this case, we're just going to use that angle right there. So in regards to the right triangle we're going to use, this one's pretty straightforward. Here's my right triangle. This is 30,000 feet. This is 570,240 feet. And I know that this angle is what I want to find. So relative to that angle, this is opposite. This is the adjacent leg. I'm not dealing with the hypotenuse at all. So again, this is a tangent problem. So we'll set it up now and say the tangent of theta is equal to 30,000, the opposite, divided by 570,240. And again, I knew to use tangent because I'm still just thinking about SOHCAHTOA. All right, and so I had opposite and adjacent, so there's my tangent. So in my calculator, all I'm going to do is inverse tangent. So inverse tangent of 30,000 divided by 570,240. So in your calculator, hit second tangent, or get that inverse tangent option, and then type that in. Oops, wrong button. And I get about 3 degrees, like 3.0115. So theta is approximately 3 degrees. And that should make sense. You know, if the plane's 108 miles away, you really wouldn't have to look up so much to see it flying in the sky. All right, it's about 3 degrees. All right, and then the last problem here is just another way. This one will be pretty straightforward and easy. Surveyors use trigonometry to indirectly measure things. So suppose you wanted to measure a distance across this lake here. Well, you know, I don't have a boat or a tape and measure long enough to do it. So I'm going to use trigonometry to determine that measurement. So here's what the surveyor did. All right, he set up 2 stakes, one here at point A, one here at point B. Then he walked 500 feet away from point B and put his little surveying tripod here at point C. All right, from here, and the way he walked away from point B, he ensured that he had a right angle here, so he could use trigonometry to do it. At this point, he finds the angle looking from between stakes A and B to be 53 degrees. So he wants to know, hey, what's the distance from A to B, or the distance across the lake? So I'm going to think about SOHCAHTOA, what's given to me, and what I need to find. So I know, let's see, this side over here is opposite the 53 degree angle. I don't know anything about the hypotenuse, so we'll disregard that. And this leg is the adjacent. So yet again, I guess I didn't get very creative here, we're going to use tangent. And so the tangent of 53 degrees is equal to opposite, which is x, over adjacent, which is 500. In this case, because the variable's on top, I'm going to multiply both sides by 500. And I'll get that x, distance across that lake, is 500 times the tangent of 53, which is about 663.5 feet. So we'll round, it doesn't say to round to anything in particular, so we'll just go, in this case, maybe nearest tenth. So the distance across that lake, 663.5 feet. So there you go. If you were okay with the first day's unit, really, guys, this is just drawing right triangles yourself and finding missing sides or angles. Again, just reach out if you have any questions or need help. Hope you're doing well.